All righty. Here we go. Section 4.4, the second derivative test. So here's the second derivative test. It's the test for concavity. If the second derivative is positive, greater than 0 is positive, that's the second derivative, then the graph is concave up. If the second derivative is negative, then that part of the graph is concave down. Can you tell me, is this curve concave up or concave down?
Up.
Count down.
It's actually up, concave up. It's like, I don't know how you would say it. Maybe the cave is I don't know how you would write it, but it's concave up. The curve is facing up. This curve is concave down.
Oh, okay.
So that's good to know. If the second derivative is positive, greater than 0, then we're concave up. If the second derivative is negative, then that curve at that spot is concave down. There's one more, I don't know if it's on a slide. I'm sure it's on a slide later on, but I'm just going to add it in here. If the see, this is greater than 0, this is less than 0. If the second derivative equals 0, this is called an inflection point. Inflection point, and an inflection point is where concavity changes. So I'm just going to draw something really quick. At this point right here, the graph is concave down. Do you see? At this point here, the graph is concave down. At this point here, the graph is concave up. And there's a point somewhere on this graph, and I'm going to call it about right here, where concavity changes. That's where the second derivative equals 0. That's called a critical value. Oh, not a critical value, an inflection point. I had it right here. That's an inflection point. And once again, an inflection point is, do you see this is concave down? And then on this side, it's concave up. This is where the concavity changes. The inflection point is where concave up changes to concave down. The inflection point. And that inflection point can be found by taking the second derivative and making it equal to 0. All right. So let's move on to the next slide. Don't forget, just yell at me and stop if you have any questions. So once again, points of inflection, here it is here, the second derivative equals 0. Or a point of inflection also if the second derivative does not exist. So just play that, make that a special note also in your notes. Second derivative equals 0 is an inflection point. That's the spot where concavity changes. Or if the second derivative does not exist, you might want to turn off your microphone so we can't hear you. I can actually mute. Okay, I did it for you. So So that's the point of inflection. The inflection point is where the second derivative equals 0. So it says determine concavity. And we're going to go through this process. So when we're going to do this, when we're going to graph this later on, the first thing we want to do is find out where the second derivative equals 0. So the first derivative equals 2x, and the second derivative equals 2. The derivative of x squared is 2x. The derivative of 2x is just 2. So can I make the second derivative equal to 0? No, because there's no x's. So the second derivative equals 0. It actually doesn't exist. There's no critical point. I mean, there's no inflection point. Because there's no way of changing 2 to 0. There's no x's left. And we'll show that by having our graph x squared, right? There's no point. Concavity doesn't change. It's always concave up. So this graph is always concave up. So, I mean, if you look at it, there's no critical points. I keep on saying critical points. There's no inflection points. No inflection points. I'm going to write it again. So I stop saying critical. If there's no inflection points, then the interval is from negative infinity to infinity. There, so we're going to mark the inflection points down on this interval. But there are no inflection points, so our graph is from negative infinity to infinity. And I'm going to choose a test value. Any test value between negative infinity and infinity. You can pick any test value. I'm just going to pick x equals 0. And if I look at my function second derivative, it says find the sign of the second derivative when x equals 0. Well, when x equals 0, this is still 2. The function's always 2. And it's positive. Remember, when your second derivative is greater than 0, when it's positive, you're concave up. That was from our previous slide. So the sign of the second derivative, when you plug 0 in there, is 2, positive. The sign is positive. The conclusion is, between this interval, we're concave up. So I just wanted to start off with a really simple one there. And that's all we're going to be doing in this section, determining the concavity, finding the inflection points and determining the intervals where the graph is concave up or the graph is concave down. Okay. Okay, I'm not going to do this one yet. I'm going to come do this one because this is much easier than the other one. So I want to do this one here. So find the inflection points and determine concavity. This is the whole section that we're did the PowerPoint give me a, did the PowerPoint say 4.7? I think that's wrong, by the way. This is 4.4. I'm sorry. This is section 4.4. It's not 4.7. This section is 4.4. So just make a note of that. Oh, that's theorem 4.0. Is there? Yeah, it says 4.4 there. Never mind then. Boy, I was confused. I thought I saw a 7 in there. Oh, no. Now it won't let me do anything. Give me a second. Oh, I made a permanent change there. All right, so for this problem, find the inflection point to determine the concavity. To find the inflection point, once again, you have to have the second derivative equal to 0. So first we have to find the first derivative. First derivative of x4 is 4. Bring the 4 in front and then subtract 1. This derivative, bring the 3 in front and subtract 1. That's the first derivative. But to find inflection points, you have to set the second derivative equal to 0. So I got to find the second derivative. Bring the 4 in front. 4 times 4 is 16, and subtract 1 from the power. Bring the 2 in front. Negative 12 times 2 is 24, and subtract 1, and you get this, x. So the second derivative...
Isn't it 4x cubed minus 12x squared?
Oh, yes, you're right. Thank you. I'm glad somebody spoke up. And so the 3 goes, let me erase. Let's start that over really quick. Thank you. We would have messed this thing all up. 4x subtract 1. I said it, but I didn't do it. And then we're going to second derivative, bring the 3 in front, 12x squared, and 24x. There we go. I hope I got it right now. 4 minus 1, 3, 12, yes. All right, so 12x squared minus 24x equals 0. Set the second derivative equal to 0. We have to find where we get 0, so we factor this. A 12x can actually factor out of both of these. Do you see I can divide both of these by 12 and x. So 12x equals 0, or x minus 2 equals 0. When I divide both sides by 12, I get x equals 0. When I bring the 2 over to the other side, I get x equals 2. So I have 2 inflection points. This is where concavity changes. So my first interval, we're going to use the entire number line. It goes from negative infinity to 0. Then we go from 0 to 2. Then we go from 2 to positive infinity. Do you see our inflection points determine the intervals? Our inflection points, and we're going to use a whole number line. Negative infinity to the first inflection point on our graph. Then our inflection point to the next inflection point from 0 to 2, and then from our last inflection point to infinity, and we get 2, 0. From here, we have to find a test value. So give me a number, anybody, give me a number between negative infinity and 0.
Negative 2.
Yes, how about something easier on the math? Negative 1. and then we're going to find a test value between 0 and 2, which is 1. And then a test value between 2 and infinity, I'm just going to pick 3. So you need a test value within that interval. All right, so I'm going to erase the stuff at the top here. We have everything we needed. And I'm going to put over here inflection points where 0 and 2. Okay, so now we have to take these test values and plug them into the f prime prime, the second derivative. Plug the test values into f prime prime. F prime prime, the second derivative, is 12x squared minus 24x. 12x squared minus 24x. And I'm going to plug the test values in there. That's what it says, the sign of the second derivative. When you plug the test value in there, negative 1. Negative 1 squared is 1 times 12 Negative 24 times negative 1 is a positive 24. 12 plus 24 is 36. The sign of the second derivative is positive at that point. Do you see? When you plug in negative 1 into that second derivative, you get a positive number. It doesn't even care what the answer is, 36. I don't care. I just want to know if it's positive or negative. It's positive. So I'm going to do this again for my next test point, positive 1. Put a positive 1 because there's my next test point. This is 12. This is negative 24. 12 and negative 24 is negative 12, which is a negative number. So when I plug 1 into the x value, I get a negative answer. And I'm going to finally do 3, my last one, 3. I'm going to plug it in. 3 and 3. 3 squared is 9. 9 times 102, 9 times 12 is, I think, 108, right? And 3 times 74, 24 is 72. So I get a positive answer. I don't even know. What was that? 36. I get a positive answer, positive 36. So the question is, we found the inflection points. Here they are. Determine the concavity. Between this interval, a positive, right, when f prime prime is greater than 0, it's concave up. When f prime prime is negative, we're concave down. And when f prime prime is positive, we're concave up. And that's all we wanted to do for this. I'm going to plug this into my calculator really quick and just take a quick look at it. So I'm going to type in this function first. Give me a second. X raised to the 4th power minus 4x raised to the 3rd power Uh-oh, I typed in something wrong. Hang on. To the 3rd power. So if you look at this graph, this is the graph we're looking at. Do you see between negative infinity and 0? Oh, sorry, you can't see the graph. Between negative infinity and 0, do you see how this graph is concave up? Maybe I can actually draw it. Draw it here. Our graph starts looking like this. Do you see? I mean, it looks like it's going to continue on. It's concave up. Do you see? It's a curve, and the curve is pointing that way, so it's concave up. And then the curve goes down like this, and between 0 and 2, between this amount of curve, you see how the curve is concave down. If we're just looking at that area, this graph, the graph is concave down. And then at some point, the graph at 2, it turns around. At some point, there's an inflection point at 2. Do you see how this part is concave down and then this part is concave up? Concave up, concave down, and then concave up. So that's what we're doing here, looking at the different inflection points and then determining the concavity within those intervals. All right, so I'm going back to the previous one now. I really don't want to do it. Wait, is that the, no, this one. So I'm not gonna, I don't want to do the work, but by the way, I'm not going to do the work. I'm just going to write the answer down in the book. But let's start off. We first have to find the first derivative. So you have to do this in the homework. It makes sense. And I mean, you have to be able to do one of these. I'm not sure if I'll have one this time consuming on the test. I'll tell you more when we get to the review, but you do have to be able to do this. Remember this, to take the derivative of this, what rule do I have to use? Does anybody know?
Is it the quotient?
Yes, the quotient rule. I just want to make sure everybody's still up on all our rules. Let's see, there we go. Back to here. So I just want to make sure everybody's up on our rules. There's wait, there is F and there is G. If F is X, if F is X squared plus 1, then F prime is 2X. If G is X squared minus 4, then G prime is 2X. And then grab your formula sheet. Make sure you have those and look up the quotient rule. Do product quotient rule. And remember, the quotient rule says F prime G minus F G prime all over G squared. I'm going to cheat. And if I can find it on here. I'm going to cheat, and it says the first derivative, by the way, you're going to write down, you know, all this and then combine like terms, and you should get, for the first derivative, I really want you to try this, negative 10x over G, which is X squared minus 4 squared. That's the first derivative. So that is the first derivative. All right, so now we're going to find the derivative of the first derivative. We have to find the derivative of this, and I'm going to erase this part here because we have new F's and G's. Once again, our F is negative 10x, and our F prime is just negative 10. Our G is X squared minus 4 squared, and now we need to know what G prime is. So I'm just going to give you a second to think about that. If G is X squared minus 4 squared, you have to figure out G prime, and you have to know this at this point. You have to know how to do this. And somebody tell me what rule we use for this?
The chain rule.
Chain rule. Just want to make sure everybody's on the same page. So if G is X squared minus 4, and I'm gonna factor G, I'm going to change squared. I'm going to change it to G is U squared. where u is x squared minus 4 and u prime is 2x. So if I mess with this, the derivative of g then is 2u u prime. So g prime is 2 times u, and u is x squared minus 4, and u prime is 2x. So g prime then is all this. 2 times, by the way, 2 times 2x is 4x, and then we have x squared minus 4. So when you then put all that into f prime g minus f g prime and all over g squared, when you do all that math, I'm not going to do it all. You combine all the terms. They factored out a 10 on the top when they finished. This is what they got. And oh, maybe I should have did this. X squared minus 4 to the third. What happened was they had another x squared minus 4 on top, and it factored out with 1 on the bottom. Do you see? Because this should be x squared minus 4 to the fourth when you square that bottom. However, there was another, it was x squared to the fourth, but there was an x squared minus 4 up here that canceled once you do it, and it changed to the third. So the second derivative, I just want you to see, I don't have all the room to show you all that. The second derivative just looks like this. This is the answer to the second derivative. Okay, so we have the first derivative, we have the second derivative. Let me verify that I wrote it down correctly. We did. I just don't have all that room. I'm going to erase now most of this. Keep on going. Lucky I'm recording this. So you have to do all that, and then you should end up with this right here. Now we have to find the critical values where, I should have put the second derivative here, 10, 3x squared plus 4 over x squared minus 4 to the third. And the question is, where is the second derivative equal to 0? Where is 10 to 3x squared plus 4 over x squared minus 4 to the third equal to 0? Can somebody tell me what x value there is that makes this equal to 0? Anybody know?
Is it square root of 4 over 3?
No, that is a good try because square root of 4 over 3, there's no subtraction here.
Oh, it doesn't exist because it would be a negative.
Exactly. Do you see, by the way, I mean, just going through the algebra for it, if I multiply both sides by the bottom, x squared minus 4 to the third, x squared minus 4 to the third, do you see how those cancel? 0 times that is still 0. So what we're left with is 10 3x squared plus 4 equals 0. Divide both sides by 10. I get this. Take the 4 over, divide by 3. I get negative 4 thirds equals x squared. You can't have an x squared equal a negative number, right? You can't take the square root of a negative number. So there is no inflection point using this method that we just did. So there is no inflection point. So I just want to show you f prime prime equals 0 produced no inflection points. However, at the bottom, x equals 2 and x equals -2 are asymptotes. And that's where, you know, it does not exist. There's a part of the graph that you can't take the derivative of. Do you see? That's the part of they're asymptotes. So that's where we're going to have our intervals from -infinity to -2. Then we go again from -2 to +2. Then we go again from 2 to infinity. So those are our intervals right there. Those are our intervals. We use those asymptotes because it does not exist at 2 or -2. Remember, we said the asymptotes, I mean, the critical numbers are the inflection where the second derivative equals 0. The inflection points are where the second derivative equals 0, or when the function does not exist, and they don't exist on those asymptotes at 2 and -2, right? 2, if you put a 2 here, 2 squared is 4. 4 minus 4 is 0. You can't have 0 on the bottom of the fraction. So now I need a test value. I'm going to pick 3, -3. I'm going to pick 0, and I'm going to pick 3. We're going to plug in those numbers into this function. I really hate that I don't have a huge board. I still run out of room when I have a huge board, but this makes it even worse for me. We're going to plug -3 in there first. 10 to the 3 to the -3 squared plus 4. Sometimes it won't let me write. There we go. All divided by x squared minus 4 to the 3rd. And we're not putting x squared in there. We're putting the actual number in there. What number are we plugging in? -3. So here is, I get -3 squared is 9. 9 times 3 is 27 plus 4. I get a positive number on top. On the bottom, -3 squared is 9. 9 minus 4 is 5. 5 to the 3rd is positive. Positive divided by a positive is positive. So like I said, I don't even care what the answer is. You could find the answer. I just want to know the sign when I plug -3 in there. The sign is positive. A positive sign for F2 at that point means it's concave up. Next, I'm going to plug 0 in there. When I plug 0 in, that turns to 0. 10 times 4 is positive. 0 squared is negative. -4 to the 3rd power is -64. It's negative. Positive divided by a negative is negative. So I know I get a negative answer here, which is concave down. We don't even, like I said, we don't even care what the number is. We just know at that point it's concave down. And then I'm going to lastly put my last test point, 3, in there. If I put 3 in there, 3 squared, all the math on top gives me a positive number. 3 squared is 9. All the math on the bottom give me a positive number. Positive divided by a positive is a positive number. So we're concave up. And I want to put this one in my calculator just to show you once again. I'm going to put that into my calculator. Give me a second. Parentheses, x squared plus 1 close parentheses divided by x squared minus 4 close parentheses, and graph it. And if we look at our intervals, from infinity to -2 right here, do you see how this is concave up? It's concave up. From -2 to 2, the graph is concave down. And from 2 to infinity, the graph is concave up. So there's a graph. Perfect. That's second derivative test. All right. Let's see what else we have.
So what is the role of the asymptotes over here?
The asymptotes tell you where in that problem, the asymptotes told you where to change, since we didn't have any inflection points, the asymptotes told you where to put the intervals. You see our asymptotes were -2 and 2. So that's where we're going to have our intervals.
So if we don't have any inflection points, how does the concavity change?
Look, the inflection points are where the second derivative equals 0. There's also inflection points on the asymptotes. That's when the second derivative does not exist. That's the same thing as asymptotes. Okay, so we call those asymptotes inflection points also.
Okay.
Since we didn't, on that problem, we didn't have anything that made it equal 0. We use those two asymptotes. You always use those asymptotes as inflection points also. I don't know why that red doesn't erase. Okay, second derivative test. Okay, so there's something else we need to know about this second derivative test, that's okay. When the second derivative at a particular point is positive, we know somewhere in, by the way, positive means concave up, right? This is concave up. That's concave up. If you look at it, concave up, that means it has a relative minimum. That's all this says. Second derivative, if you do a test point and it's positive, you know it's concave up and that there's a relative minimum at that critical number. See, at the critical number. When the second derivative is negative, we know it's concave down. And if you look here, this is concave down. But that point right there is a relative maximum. It has a relative maximum in there. In that concavity, it has a relative maximum. And you got to be careful about this one. When that second derivative does equal 0, the test fails, and you can't tell if it has a relative minimum or maximum. You have to go to the first derivative test. And if you watch those videos on the first derivative test, the first derivative says, oh, this is a positive slope. This is a negative slope. So that's a relative maximum. If you look here, if you go from negative slope to a positive slope, then you have a relative minimum. The first derivative test on those other videos that I did shows you that a negative slope to a positive slope gives you a relative minimum. And then from a positive slope to a negative slope, it gives you a relative maximum. So those are from the other video, the previous ones. And I think that might be, I don't know if that's it here. I'm just trying to go to the next. That's not helping me. There we go. Are we done here? Wait, where? It's not moving anymore. Oh, this is it. Okay, so this is the last one on this section. Use a second derivative test to find the relative extrema. So we want to know if it's a relative minimum or a relative maximum. So we're going to do the same thing. First derivative equals negative 15x4 plus 15x squared. That's the first derivative. The second derivative equals negative 60x3 plus 30x. We have to find out where the second derivative equals 0. And we have negative 60x3 plus 30x. Factor out a 30x. And I get, actually, you can factor out a negative. I like to factor out a negative. If the first term is negative, factor out a negative. And I get 2x squared minus 1. So I factored out a negative 30, divided each of those by negative 30, and that's what I got. So to find where this equals 0, negative 30x equals 0, so x equals 0. That's one inflection point. The other inflection point, 2x squared minus 1 equals 0. Take the 1 over and divide by 2. I get x squared equals 1/2. Square root both sides. X equals the square root of 1 over the square root of 2, which really equals 1 over the square root of 2. And this is okay answer, but you could also, I think, to clean it up a little bit, if you remember algebra, you don't have to. I'll accept this. If you multiply it by 1, you get the square root of 2 over the square root of 4, which equals 2. Do you see? 1 over square root of 2 is the same thing as the square root of 2 over 2. So our first inflection point, our first intervals is from negative infinity to 0. Then we go from 0 to the square root of 2 over 2. And then we go from the square root of 2 over 2 to infinity. So those are our intervals. Find a test point in there somewhere. -1. Square root of 2 over 2. It might be easier just to type that in your calculator first. Just to show you, the square root of 2 divided by 2 is 0.7. You know, this is somewhere around 0.7. So I can do a test point between 0 and 0.7. Let's do a test point at 0.5. And then here, if it's 0.7, I can do a test point at 1. You know, it's more than 1. So from 0 to 0.7, I'm choosing 0.5. And then 0.7 to 1, infinity, I'm picking 1. And then I'm going to plug the sign into those, into the second derivative. So I'm going to first plug -1 into here. I'm going to erase this now. -60 plus 30. And I'm going to plug 1 into here, or -1 first. Our first test point is -1. I get 60 minus 30, which is a positive number. Here I put the next one I'm putting 0.5 in there. 0.5, 0.5. I get negative 30 here, plus 15, and that's a negative answer. And when I plug 1 in there, I get positive, a negative and a positive. I get a negative answer again. Well, let's go through the whole process. When I plug 1 in here. Oh, wait, I was supposed to do to the third power. I didn't do that. 1 to the third power, I'm sorry, is negative and positive. So that's negative 60 plus 30. So this is negative. I didn't, let me make sure I got this one right. If I put 0.5 in there. 30 times 0.5 is 15, but negative 60 times 0.5 raised to the third power is negative 7.5. So this is negative also. Where is this at?
That's not a positive. Negative 7.5 plus 15.
Give me a second. I think I did something wrong here. I think I did oh no, I did the second derivative correct. Something is not right on this problem. Give me 1 second. Using the second derivative test. Okay, so I'm going to erase this whole thing. I apologize. I have this interval here, and it's not, for the second derivative test, we don't use the interval. I'm looking at this now, and my slide is wrong. And I noticed something was wrong when I saw points. And previously, we didn't use points. So I'm going to show, I'm going to redo this one. I apologize. I'm going to redo this one. Well, on the second derivative test, the points are critical numbers. The points, these I'm going to write down here. The points are critical numbers. So we're not using intervals for the second derivative test. We're using points, and those are critical numbers. Once again, if I look at this, graph right here, can somebody tell me where the critical numbers are? Not inflection points, but critical numbers. Can anybody see the critical numbers? Critical numbers are relative minimum and maximum. Those are critical. The critical numbers are in red. They're minimum and maximum. Now, critical numbers are when you take the first derivative and make them equal to 0. That's what we learned previously. Now, the second derivative, when that equals 0, those are inflection points. Inflection points are these right here. That's where the concavity changes. Do you see how concavity changes? The inflection points are in black. The critical numbers are the valley and peaks. So what we need to do is find the critical numbers first. And the critical numbers is when we have the first derivative. They should have did a separate section of this. And set the first derivative equal to 0, negative 15x to the fourth plus 15x squared. Set that equal to 0. I'm going to put a negative 15x squared out of here. I end up with x squared plus 1 equals 0. So I have negative 15x squared equals 0, or, oh, by the way, I don't know if you noticed that error I made. That should be negative. I'm factoring out a negative 15, so this turns positive, and this one turns negative because I'm factoring out a negative 15. So I get x squared minus 1 equals 0. Take the 1 to the other side, x squared equals 1. And then square root both sides, x equals 1. These are the critical numbers. X equals 0 and x equals 1. So our points are, oh, by the way, is this correct?
So we're no longer taking the second derivative?
Yes, we are. Just give me a second. Yes, we are. But when we find, we're, the previous problem, I don't want to go back to the previous problem. The previous problem said, use the second derivative to determine concavity. This problem says use the second derivative to find the relative extremas. There's two separate problems. Concavity, we're doing everything where we're doing the intervals. Extremas are the highest points and lowest points. Relative extremas are valleys and peaks. To find extremas, first we have to find the points, the critical numbers, and we found those. Somebody tell me why. Here's one critical number. Here's one critical number. I'm missing one critical number. Can somebody tell me what it is?
Could it be -1?
Yes. Right, when you take the square root of a square, you get x equals plus or minus 1. You get, so our critical, these are our points. These are our points. We have 1 point, and I'm going to go to the far left.
Do we have to establish a domain before we move forward?
No. Well, the domain is all real numbers. Look at the function. Domain can be anything. So there's the first point. The next point, x is 0. And then there's the next point here, x is positive 1. Now, when you plug now what they want is when you plug -1 into the original problem, this is our point. When you plug -1 into the original problem, what does y equal? Plug a -1 in here, plug a -1 in here. In the original problem, I get 3 minus 5, I get a -2. If I plug 0 into the original problem, I get a 0 for. If I plug 1 into the original problem, I get -3 plus 5, I get a +2. So these are the points. These are the coordinates, but these are the coordinates where our peaks and valleys are of our graph. If I was gonna, I don't know, well, I can kind of draw this graph. It's an x5 negative, so it kind of looks like this. It might have another turn in there somewhere. But it's telling me I have a peak or a valley. One of them's at -1, one's at 0, and then one's at 1. So I'm not sure how I drew it. We're going to look at the picture here in a second. But these critical numbers are the peaks and valleys. When we plug -1 now into the second derivative, now they want us to plug that number into the second derivative and tell us if it's positive or negative. So I got to write the second derivative. The second derivative is negative 60x3 plus 30x. And we don't have to factor this out. This is the second derivative, negative 60x3 plus 30x. We're going to plug these points into that graph, just the x values. If I plug negative 1 in here, I'm going to change the color. If I plug negative 1 in here, negative 1 to the third is negative. That gives me a negative and a negative is a positive 60. Negative 1 here is negative 30. I get 30. I get a positive answer. When I'm plugging negative 1 into the second derivative, I get a positive answer. If I plug 0 in the second point, plug 0 in to the second derivative, I get 0 plus 0, I get 0. I don't get a positive or I don't get a negative. And if I plug in the last number, 1, 1 to the third is 1, this is negative 60, and this is 30, I get a negative answer. So the conclusion for this, if this is positive, then this point is a, do you remember what it said in the previous slide? Go back, where's that previous slide at? I just want to make sure everybody's, where is that? Here it is. If you plug that point into the second derivative and you get a positive answer, you're at a relative minimum. If you plug that point into the second derivative and it's negative, you get a relative maximum. And if you plug 0 in and you get 0, if you plug that point in and get 0, then you have to write the test fails. Remember, I'll go back to those rules here in a second. The test fails. So that's all they wanted, relative minimum, test fails, and relative maximum. What happens when the test fails? You have to go back to the first derivative test that we learned in the first derivative test. If you plug in a number before 0 and then plug in a number after 0, if it goes from if you plug in a number before, I'm looking at a number line again, here's 0. A number before is -1, and then a number after it would be +1. If you plug -1 into the first derivative, once again into the first derivative, you end up with -1. Oh, that's a bad number. You got to plug in something like 1/2, something that won't turn to 0. Plug in 1/2. Oh, because those numbers are there already. Plug in 1/2, a -1/2, and a +1/2. -1/2 into the first derivative. -15 times 1/2. 1/2. Negative. If you plug that in, you get a positive, or you get a negative here. You get negative, oh God, I gotta plug it in. -15 times -0.5 to the fourth plus 15 times -0.5 to the second. I get a positive number. And by the way, when you plug in a positive number, you also get a positive number. So on this side of the number, we get positive. And on this side of the number, we get a positive slope. In other words, there's no relative minimum. If you remember, if you get a positive slope and a positive slope, there's no valley or peak. There's no valley or peak. This is a positive slope. This is a negative slope. There is a peak. Or if you had a negative slope and a positive slope, then you get a valley, a relative minimum. But if it says if the test fails, go back to the first derivative, we got positive, positive. So there is no relative minimum here. So I would write no, uh-oh. What happened to my computer? There it goes. Oh no, I don't know what happened. Yeah, I have no idea what just happened. Anyway, let's put this onto my calculator really quick, and we'll take a look at that. Our graph is y equals -3x raised to the 5th plus 5x raised to the 3rd plus 5x raised to the 3rd. And I'm going to close my window a little bit so we can see it better. It's pretty good. And let me bring up my calculator. So if we look at this on the calculator, if I can figure out how, there we go. If you see, what were the points again? Right here at, I think it was right, -1, we have a relative minimum. At +1, we had a relative maximum. And at 0, do you see how the slope, you see relative minimum, positive slope, negative, or a negative slope and a positive slope gives us a relative minimum. Here, a positive slope and a negative gives us a relative maximum. But here, it failed because we have a positive slope and a positive slope. It doesn't give us a relative minimum or maximum. So the first point gave us a relative minimum. The last point gave us a relative maximum, and the 0 gave us no relative minimum or maximum because we had two positive slopes and it didn't give us a valley or a peak. So that is